Okay, good afternoon. Welcome. This is part of our current dedicated lecture series. The order is a little bit reversed in that the public lecture did not happen last night, but will happen this evening. So I encourage all of you to come to the lecture at 6 p.m. Our speaker today, the delegate of the lecture, is Takashi Tokieda. He's Director of Mathematical Studies at Trinity Hall, Cambridge. He's currently the Franklin Visiting Professor of Mathematics at Stanford University, and as I said, our dedicated lecturer for this season. His title today is Chain Reactions.
Happy Chinese New Year, and thank you for braving the snow to come here. I'll start with an experiment. Can we have the, we don't have to have the camera actually, so you just watch exactly what I'm doing. Here is the cheapest chain that I could find on Harvard Square. I think I paid $3 for the entire length, which is about 10 meters, precisely because I had only $3 in my pocket at the time. And I put it in a cup. And when I hold this cup up like this, with my finger, stopping it. And when I release my finger, of course, the chain under its own weight will start going out of the cup, flowing out of the cup and just down to the floor. But that's not the only thing that happens. You'll see that mysteriously and spontaneously, the chain will start rising upward like a fountain, although there seems to be no upward force coming from anywhere. Here we go. What the? Can we have the slides, please? That is really strange. You know, you start, release, and then you get this fountain. What makes the chain stand up? Now, while I'm doing the next thing, you have to listen to me from voice coming from below. You are probably wondering why I'm kneeling in front of you. Well, apart from the worship that I owe this distinguished audience, I have to put the chain back into the cup in a very meticulous manner, because you see there's a phenomenon whereby if you dump a pile of chain into a random pile, with high probability it gets entangled. That itself is an interesting phenomenon, but that's a topic for another talk. So I'm putting the chain back. Now, this phenomenon went viral on the internet. Somebody called Mold put it up on YouTube about 2.5 years ago, maybe 3 years ago, and lots and lots of people got excited about this. Around that time, Steve Strogatz of Cornell University sent me that link, as well as to Mark Levy of Penn State, because it had something to do with a class of phenomena that we had been considering for quite a long time, and it turned out to be the beginning of this story. In the meantime, around that time, and still today to a certain extent, there was a very wide consensus among good scientists as to what was happening. You see, roughly the explanation went as follows. When the chain came out, said most people, the chain has to go over the rim of the cup, and thereby has to round a very sharp corner. Yeah, very sharp corner suddenly. And the chain doesn't want to round a sharp corner. A chain wants to round a gentler corner. So how do you do this? Well, you stand up to make the radius of curvature much larger, and then you can go around more gently. You can call this centrifugal force explanation, if you like, because you see, you can't go right like this. It's being swept out and pushed outward by the centrifugal force. Unfortunately, charming though this explanation might sound, this explanation doesn't stand up to scrutiny, as it were. In the light of a 19th century theorem, which was widely known towards the end of the 1800s, but which has since been forgotten. Here it is. It is that, let's consider the following problem. Everyone in this room has studied what the hanging chain shape is. If you support a chain at 2 fixed points in gravity, it hangs in a very beautiful catenary. In terms of Cauchy, you can describe it. Let's think about a dynamic analog of the static problem. What do I mean by dynamic analog? Well, there are different interpretations, but imagine that there are lots of, say, tubes or the rods spinning, driven by motors, and while you have those spinning tubes, you hook this loop chain on some of those spinning tubes. Well, driven by those tubes, the chain will start flowing in space. And the question is, what is the dynamic equilibrium shape along which the chain flows? Yeah? Or if you like, an equilibrium, a relative equilibrium shape. Well, you can think of many, many different possibilities. But the fact of the matter is really striking. It turns out that any shape can be taken by a flowing chain as a neutral equilibrium configuration, as the statement says. Any shape. I'll correct that statement slightly in a moment, but any shape is fine, provided the chain is flowing fast enough. How fast? I'll make that precise also. So you can see this in an actual experiment. You know, for example, you can put the rod, and just a single rod is spinning, and you can hook this very chain on this rod, and depending on accidents of initial conditions, it will start flowing in some shape. And when it does so, once it gets going, you can walk in and with your fingers mold the shape of the chain like this, for example. And when you remove the fingers, you are delighted and surprised to find that chain keeps flowing in this shape, in perfect levitation, in space, yeah? For quite a while until gravity takes over and makes the whole thing sag down. So indeed, any shape is in neutral equilibrium. I'd like to begin by proving this result very quickly, and here's the diagram. Let's look at the small piece of the chain, which I denote by ds. At that point, chain is curved, so it's looking into a center of curvature with radius r. Now, let's look at the tension along the chain. I call it the tension. You know, in continuum mechanics, tension really means force per area. But here, I'm really talking about the force itself. So dimensionally, it is the force rather than stress. This tension, pulling force, pulling things apart, varies from point to point. So I'm going to allow the variation dt. And this force has a normal component looking towards the center of curvature. And that balance is this. So you have sine d theta over 2 factor. And if you add those two tensions, you get t d theta, and that's TdS over r. OK. Remember that ds is, of course, length. So length over length, dimensionally, that's just force. So this tension, normal inward tension, must balance the relative equilibrium, must balance the centrifugal force. What is the centrifugal force? I denoted by rho the density, but please be careful. This is mass density per unit length, not per unit volume. Yeah? So per unit length of the chain, it has some number of grams and so on. This is rho. So rho is mass divided by length. Okay, so this is the mass density divided times, of course, the centrifugal acceleration, v squared over r, and that must balance what we have just computed, t over r. I'm just dividing by ds because this is per unit length. At the same time, I introduced this funny notation n. I apologize on behalf of the 19th century mathematicians. This is the external force that's coming from, for example, typically a gravity. Why n? Maybe external. I don't know why n, but it's a traditional notation. Okay, it is time now to specify what I mean by flowing fast enough. Flowing fast enough means this condition. This motivated by the desire to neglect this external effect. So suppose that you can just think, well, gravity doesn't matter, it's small correction, and we just want to see the balance of this phenomenon, really in essence, and I want to work with this equation rather than that equation. Well, that's possible if v squared is large enough compared with the right-hand side, which is Rn over rho. Or, if you like, there's a much better physical interpretation. It's saying that the half rho v squared, if you like, that's the kinetic energy density, must dominate large enough compared to what is something like the potential energy density, Rn, if you like. Anyway, so the kinetic part is large enough so that you can work with no external force. In that case, you see, wonderful thing happens. R cancels out from both sides. So the equation that you get that characterizes the balance of this chain in flowing neutral equilibrium is that the tension must be approximately, in good approximation, rho v squared. Please check the dimensions are correct. Rho is mass divided by length, and v is, of course, length over time. So if you multiply this, you have the dimension of force, which is mass times length over time squared. Good. And what is really, really striking is that r disappeared from the equation. You see, r was radius of curvature of this problem, was the only parameter that represented geometry. Yeah? Geometry has completely disappeared. In other words, it doesn't matter what shape it is. The dynamic equilibrium is satisfied provided the tension balances this how fast you're going. So geometry doesn't matter anymore. That's why any shape is in neutral equilibrium. And we can say, therefore, that it's a superstition that the chain finds it harder to round the sharp corner, but finds it much easier to round the gentle corner. It's not true. A chain can round any corner, you would equal is in neutral equilibrium. Having said this, can we have the camera, please? I have to issue a little proviso before we go on. I said, thank you. I said any shape. Actually, there is an almost obvious correction that we have to make that statement. You see, a chain cannot be bent smaller than a certain scale. Can you zoom in if possible? You can zoom in. Yeah, zoom in all the way in, all the way in. So here. So when I tried to squeeze the chain to a small shape, this is the minimum radius to which you can squeeze the chain. If you try to squash it any further, the chain has to break. So there's a minimum radius to which you can squeeze the chain. However, above that minimum radius, the chain offers no resistance to being bent. You can see that you can bend it in any shape, and then chain just stays there. There is zero energy cost associated with being bent. In other words, if you think of this as the bending stiffness, resistance to bending, the chain has this absolutely singular behavior in terms of bending stiffness. This bending stiffness as a coefficient above a certain radius of curvature, this minimum curvature, is 0. There's no resistance to bending. But below, it's infinite. That's one heck of a Heaviside function. It's as nonlinear as you can dramatically be. And this is going to be the main dramatis personae of this talk. Can we have the slides, please? Thus, we are back to square one, as it were. So what makes the thing stand up? It's not true that this centrifugal explanation will stand up. In fact, it doesn't. What is the alternative explanation? And the answer turns out to be what we call anomalous reaction. Clearly, I should come up with some sexier name, otherwise it will never take off. And as I say, this singular bending stiffness is really underlying all this. Let's then explain what this anomalous reaction is. You see, we have been growing up, some of us longer decades than others, learning that when you press on something, that something pushes back at you. Action and reaction equal in opposite directions. And also, when you pull at something, that something pulls back at you in order to resist your action. However, they turn out to be situations in nature, and also in engineering situations, you can cook them up, where when you press on something, that something pulls you in as if to help you. And when you pull, it pushes out in apparent violation of Newton's third law. Of course, there is no violation, but you have to look really carefully to understand that there's no violation. It turns out that the system might be multi-component, for example, and when you press on one component, the other components behave as if, and so forth. But this is really the key. Anomalous reaction, apparent, if you like, anomalous reaction in apparent violation of Newton's third law. You see here, in particular example, the chain fountain, the gravity is pulling you downwards, as often happens in Stony Brook, and in reaction, the chain is going upward in the opposite direction, not in the correct direction. Okay. Let's then understand this anomalous reaction in the simplest toy model, which goes actually to the heart of this matter. Imagine that you have a rod falling from above, and it's falling, and it's in free fall. And let's intercept this fall. Suddenly, boom. Well, if we intercept the fall, our intuition says that we're going to decelerate the fall. But not at all points. Let's say that it hits the floor here. Upon impact of one end, this rod suddenly spins like this around what is called the center of percussion. It's not the center of gravity, but anyway, it spins so that the other end, boom, gets tugged down. So if you have been observing only the other end, you have this really weird impression that, oh, it's been falling, free fall very happily. But as soon as you hear the bang over the collision, it starts going down faster. So by intercepting, you accelerated the fall. And there is a beautiful experiment that I'm going to show you. Excuse me. So when one end impacts, the rod flips and the other end accelerates downward. I'm going to show you a movie that was made by Andy Ruina of Cornell University, one of the people with the greatest mechanical intuition in today's world, I think. Can you see what's going on? Okay. So this is a movie of two rope ladders that are falling down in slow motion. The right ladder will be allowed to fall through with nothing stopping it, just freely, but the left ladder will be stopped by a table. And it is the left ladder that's been stopped by the table which starts falling faster. Oh, that's weird. That's weird, but we who have understood that rod model also understand this weird phenomenon. The point is that those rungs of the ladder are tilted in alternating fashion. And when this end, the lower end, hits the table, the rung spins and the other end tugs the rope down. So you get tug, 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 tug in alternation. This is, ladies and gentlemen, is a compressive situation that develops tension, which flies in the face of engineering wisdom. Of course, in a compressive context, you have to have pressure, but here you get tension out of a compressive situation. Boom, boom, boom. And this is what is going on. Now, I'm going to go back to the slides. What I'm suggesting then, I hope I can do this. So how do I go to the full screen view? Full screen mode. Thank you. Here we go. So what I'm suggesting is that you imagine this movie being run backwards. You see, if you run it backwards, you are picking this ladder off the table. And then you say, that's strange. I have the impression that it's coming down faster than I thought. Huh? Where is that faster business coming from? It comes from the anomalous reaction. In microscopic model, what's going on is the following. Well, you see, this chain is a concatenation, etymologically the right word, of beads. But think of a chain that links together those rods. Okay? This argument basically works for proper chains like this also. So if you have a stack of rods like this, and then you take the top one and suddenly pick up one end, well, you are spinning it. And the other end goes bang in collision. And that bang means that the pile underneath is giving you an upward kick in reaction. That's an upward momentum. And you go bang, 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 bang. Those upward kicks build you into an upward momentum, which makes the fountain. Now, of course, John Morgan himself in the first row is very suspicious of this kind of picture. So we have to analyze whether this explanation also stands up to scrutiny or not. But this is the basic picture. You have this anomalous reaction which comes from a bang, and then you want to go upward. Let's note, in all this discussion, what is really central as an assumption is the bending stiffness. Indeed, if you have a rod and you pick up one end, I said, well, the other end goes down and goes bang. Well, suppose that the rod were very, very soft. You pick up one end and the whole thing and curves up. Well, then there's no bang at the other end. So it's absolutely essential for our purposes, for this mechanism, that the rod, this small part of the rod, should have a bending stiffness, rigidity, so that when you pick up one end, the other end works accordingly. Yeah? So this localized, very singular bending stiffness is crucial to the following discussion. Here it is. Let's do a calculation and see if this works. I took a cartoon picture of a small part of the rod or the chain of length L. You'll see that I put in a length scale, but this length scale will disappear later on, rather luckily for us. And just so as to budget for the possibility, I mean, maybe it's a crazy possibility, but the possibility that there is such a thing in the universe as an anomalous reaction, I denoted that by R. R might turn out to be 0 after all. But the normal part of the ordinary part of the tension is denoted by T0. Okay, so T0 plus R is a priori the entire tension, which we showed is rho v squared. That was one of the red boxed formulas earlier on. So as I emphasized, R might turn out to be 0, but our business to see what R comes out to be. Okay. Next, let's sort of look at what's going on. First of all, let's calculate the torque that those forces, upwards tensions are exerting. Well, in order to do so, what's the force divided by mass? Well, force is rho v squared. As I said, it's a tension. And then mass is, remember, rho is linear density. So rho times length is mass. So divided by rho v is acceleration. But we are interested in the torque. So what is the torque? Torque is, of course, the arm of the force acting times the force. Or if you like, the acceleration times mass. So if you have to, if you want to do the torque, you have to divide this by the arm of the action, which is half of this. So that's L over 2. Okay? So that's going to get you the angular acceleration. So the torque balance reads as follows. You see, T0 is trying to spin the whole thing counterclockwise. So there's a positive sign. And R is trying to, if it exists, spin the whole thing clockwise, so it has a negative sign. So that's the torque. And the right-hand side, the coefficient, funny coefficient, is what is called the moment of inertia, which you can calculate easily. It always has the dimension of mass times area, so this is the right dimension, times this is the angular acceleration that we have just obtained. So if you simplify, it's 1/6 of rho LV squared. Now, note that at this stage, L cancels out of the equation. That's very nice. Anyway, we have two equations. The top one, T0 plus rho R equals rho V squared, and this bottom one. And two unknowns. We can solve these equations. Thank you very much. And there's a unique solution. Unique solution shows that of the total tension that we calculated, rho V squared, the famous rho V squared is sort of partitioned or distributed into two parts. One part goes into the ordinary tension, that is T0, that's 2/3. But the other part gets 1/3 of its share, and that's R. R came out to be positive, non-zero. So this is a typical situation. Whenever you have this kind of situation, you get some of the tension, to be sure, in majority, 66% into the ordinary part, but a little bit, non-trivial bit, goes into the anomalous reaction. And please note that because of the cancellation here, the result doesn't depend on L anymore. So this is good news, because until now, we didn't know. I mean, this model might be applied to all sorts of complicated situations where the details of geometry are different. But because L disappears at the end, we don't care really what the details of geometry are. Actually, you can even take the continuum limit as L goes to 0. And then there's no problem with the singular limits, because L doesn't appear simply. OK, so that's a wonderful news. Before we go on, so we have now harvested this result that the anomalous reaction gets 1/3 of the total thing. But let me point out that this thing is also a very, very dissipative system. I mean, I used to come from Hamiltonian perspective, but you can hardly do Hamiltonian mechanics like this, because when you're pulling up this chain, there's a pull up, so there's a force, and the chain is following. So you're pumping in a lot of work or energy into the chain. How much energy? Well, the tension is rho V squared, and by time dt, you are pulling up the length of v dt, so that's the length over which the force is acting. So the work that you pump in, divided by t, you get power. Power that you're pumping in is this quantity. But not all of that energy is kept by the chain. Indeed, the kinetic energy of the chain is, of course, the mass, which is this, times v squared, and 1/2. You see that the latter expression is exactly half of the former expression, which is to say that whatever energy you pump in, half of it is completely dissipated, automatically dissipated, and on the other half is being used as kinetic energy. It's a dissipative system, because each time you have this bang, 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 collisions, that dissipates the energy and wastes exactly half of the total energy that you are putting into the system. So very dissipative. So let's go for the throat. I want to calculate how high the chain fountain will go up in this idealized model whenever I hold it in some configuration. For example, let's say that the depth to which you are allowed to fall is capital H, and the height to which you are going to rise is small h. Yeah? Small h might turn out to be 0, but I'm doing the calculation. So here, I'm holding up the cup, rather more handsome than the real thing. And then you have this chain going up and coming down. Let's say that across the top, you get the tension, which is T. And on the left side and on the right-hand side, we're going to look at the balance of nature. On the left-hand side, you see, there is T pulling at the top, at the peak, but at the bottom, you have the ordinary part of the tension, as well as this thing, this weight of the chain, which is on the left, that arc. And because the height is h, where I'm approximating this pretty much vertical, rho g will give you the weight. On the right, in contrast, nobody's pulling at the bottom. The chain is just dropping on the bottom and accumulating. Nobody's pulling at the bottom, so there's no tension part, and that's the weight on the right-hand side. So they are balancing together like this across T. At the same time, we have already figured out that T is rho V squared. Well, you can actually do all the calculations at this stage. And the calculation, you see, in terms of those things in the box upstairs also, should be expressed in terms of dimensionless parameters. So how high does the chain rise? How high compared with what? Well, compared with the depth to which the chain is allowed to fall. So this is small h over large h. And it's easy to see that it's 1/2 in this approximation. Also, although we were not going for this, it's fun to harvest another thing, which is the speed at which the chain starts going. Clearly, depending on how high I hold the cup, it starts going at some speed. I don't know how to calculate this, but nature does. And it turns out nature also tells us. What's a good yardstick for the reference for the speed? It's, I think, square root of 2gh, because that's the speed at which if you drop something on the floor, at the moment of impact, it's going at that speed, yeah, because of the kinetic and the potential energy balance. And compared with that typical scale, v has this size of square root of 3/2. Yes, you have noticed it has sine and cosine in it. Okay. At this stage, at this juncture, we seem to have finished the job, but in fact, we have to do one more thing. You know, I'd like to insert a little speech about the concept of rigor. You often hear pure mathematicians, you know, very proudly say, oh, I am very rigorous. And then you hear applied mathematicians very proudly say, oh, I'm totally unrigorous. I think both attitudes are based on a childish misunderstanding. You see, perhaps your concept of rigor means that you make an unbroken chain of logical deductions all the way back to some pedigree, for example, like axioms of Zermelo-Fraenkel axiomatic system, or something else. But surely what really rigor means is a set of, say, disciplined attitudes or good habits of work, or indeed a set of protocols which enable you to prevent yourself from fooling yourself. Yeah, avoid fooling yourself. That is, minimize the risk of fooling yourself. That's surely what rigor means. And in applied mathematics, there is, in fact, its own rules of rigor. And it means, first and foremost, to check whether your model is reasonable against the experiments, against the hypothesis that you have been making. And here, our key hypothesis, in case you have forgotten, was that the chain is going fast enough. Otherwise, this sort of balance and so forth were not justified. So we have to check whether our model is reasonable. And that condition was given, I recall here, v squared is fast enough if you like a kinetic overwhelms potential. Well, if you plug in all the expressions, it comes out to be the following expression. So here the n, the external force, is of course the external gravity. And so the condition after some calculation reduces to large h being much greater than small r. So what was large h? It's the depth to which I'm allowing the chain to fall. And small h is that radius of curvature at the top. And you have seen with me when I did the experiment that, you know, radius of curvature was maybe like this. And the fall was maybe a meter or more. So this is certainly correct. And so the entire model stands up to scrutiny. Okay, so we have to check this kind of thing. But this is the great harvest for the first half of this talk. Now,
an experiment, say from the second floor balcony,
excellent.
Drop down, it would.
I'm so glad you pointed this out. I should buy you coffee afterwards. So because I had exactly $3 in my pocket when I went to Dixon's hardware store on Harvard Square, I could buy only this amount of chain. But you should go back with $30. And if you do this experiment, and from, let's say, third floor balcony, let's go for the third floor, then you get a magnificent high chain fountain. And there's a video footage involving Biggins on the internet and so forth. Biggins, by the way, was a postdoc at my college in Cambridge, and he's really a smart guy. And he wrote this, published this Procroy-Sock paper with Mark Warner, based on this toy model. Okay, yeah. So you should go for that. Now, I would like to show you, shall I say, an extension of this business. And can we have the camera, please? Which is, in a way, even more surprising. We are going to stop doing things vertically, that's my Japanese culture, and start doing things horizontally, that is English culture, American culture. And in order to do so, I'll set up the experiment. And you'll see while I'm setting up what I'm doing. I'm laying out on the table a chain in a zigzag, going back and forth fashion, but at constant width, like this. Yeah. And in a monolayer. By monolayer, I mean the chain never goes over itself. It's always one story high. Yeah? Now, you are probably all getting bored and thinking, well, you know, this is really a silly job Tadashi is doing. But you know, you think so, but before, you notice that I'm pulling the chain out of a cup, prepare the cup. Well, before I invented this technique, it used to take 10 minutes for me to do this, and then I would mess up the final configuration after all. So I'm very grateful that I came up with this experimental technique. And you should have a lot of respect for experimentalists in general. And so,
We're filling the cup in a certain way.
yeah, so
Tightly coiled to take advantage of the.
no. On the contrary, it's very loosely sort of settled from the top because any tight coiling or random sort of coiling will get it completely stuck. Yeah, so you want to avoid entanglement. Yeah? And in fact, entanglement is with probability very, very close to 1. It's impossible to avoid if you just dump the chain. Yeah, so I'm just pulling it out. I don't know if you saw, because when I was kneading in reference to you, so I was sort of putting it in. Okay, so it's going to take another 45 seconds or so. Please be patient with me. And by the way, about the going vertical and horizontal, while I'm doing this, let me give you a little anecdote about the Japanese. It's about the perspective among languages. You know, Japanese arrives in Israel, and not knowing Hebrew or English, decides to take lessons in both. And after a few months, he's asked by his friends how he's getting along with the Hebrew and English, and he says, oh, wonderful, the great big similarity between Hebrew and English need much help. And they're really puzzled. What similarity between Hebrew and English? And Japanese says, well, both horizontal language. Anyway, it's a question of perspective. Okay, I have just finished making this arrangement. Thank you very much for your patience. Now, let me comment on this. It is a horizontal arrangement, as you can see. And what we shall do is to start pulling the end of this chain out horizontally. In practice, because I'm lazy, I mean, I should be doing this, of course. But because I'm lazy, I'm going to dump the end of the chain on the floor, and the chain will be pulled down, and need to pull the chain horizontally out. You might wonder, you might indeed be suspicious that, well, on the edge of the table, the chain turns a sharp corner, so maybe that disturbance will affect the experiment. I'm going to convince you later on in talk that this kind of disturbance has no effect on the physics or the mathematics of the problem. And indeed, I'm going to show you some videos in a moment where we pull the chain really artificially out horizontally, so there is nothing suspicious going on there. I haven't started cheating yet. Okay, so to summarize, you have a completely horizontal arrangement because it's monolayer. There isn't even second story. And then the external stimulus is also horizontal. It's being pulled out horizontally. So it is a purely horizontal problem. It's 2D. There is no vertical component of anything anywhere. However, you'll see that when I start pulling this, a strange vertical arch starts standing up in the vertical direction. Here we go. Did you see? It's not so prominent because the table at the Simons Institute is very slick and slippery. But let me show you the movie that was taken by Will Steinhardt at SEAS at Harvard. You think that there's nothing happening because this is sorry. Can we have the slides, please? Sorry. Okay, so this movie was taken as well as the other movies by Will Steinhardt at Harvard. And you think that nothing is happening because it's 1,000 frames per second. And I guarantee that this is just being pulled out horizontally, and it's exactly the same kind of configuration you saw before. But soon, you see something happening. And what you see is, I call it a curl, little curly region, which sweeps the whole thing back and forth. And the chain wants to stand up soon enough, but the first time it fails. You see, it wants to stand up a little bit, but it gives up. Yeah, here. But then, next time it tries, now it knows how life works. It stands up, and then it goes completely crazy. Look how twisty the root is, first of all. Yeah, root from which the chain. And then the arch is very stable. That's understandable in the light of that 19th century theorem that I mentioned. You see, once it gets going fast enough, any shape is in neutral equilibrium, so that the arch is fine. So it goes, and really fantastic picture. Goes back and forth, extremely stable arch that stands upward, although this is a purely horizontal problem, a priori. And the end is rather funky. The end the tail of the chain comes in, whipping in. It's very nice. Keeps going forward and backward, forward and backward. Yeah. Now the end. Watch. Whoosh. That's very nice. Okay, so that's what it is. Now let me finish putting this. So this is a remarkable thing. How?
Picture like the loops were being pushed away from the direction that the chain.
Yeah, good. Yeah, we'll come back to that. So the root of the arch, where the arch is standing up, is really key to the analysis of the problem. Yeah, it's really a fantastic thing. Okay. Can we have the slides, please? Oh, before the slides, can we have the movie again? I'm going to, because we're among grown-ups, I'm going to show you another movie, which I don't often show, but which is quite curious. I was keeping, only among friends and experts. Okay, I was keeping something up my sleeve. When I made that horizontal arrangement, I took a constant width of certain width. It was maybe yay large. It turns out that if you make that arrangement with too wide a width, no standing up occurs. So there's a window within which you have to work, it turns out. And we'll try to understand, we don't quite understand why that window exists, but we kind of understand on the metaphorical level, but there's a window within which we have to work. So here, what I have made is a very, very ridiculously wide arrangement. And then I narrowed it down and then widened it again. But even at the narrowest passage, this is way outside that window. In other words, if you take any width that you see in this picture and make a constant width arrangement with that width, then it's not going to stand up. No chance. But what we have created here is a passage through a minimum. There's, in the geometric sense, a criticality of the configuration. And really strangely, this critical configuration in the geometric sense seems to aid this standing, abet this standing up. Let's go. Here you see the picture even better. It starts going back and forth, back and forth. And you'll see that there's immediately a curl that forms. And no, I don't want to run anything from. And you see a curl is sweeping back and forth and calls in the next curl from the end. And soon there's an accumulation of curls. So you see there are two curls that are sort of traveling together, and third curl joins, and so on. But while curls are accumulating, nothing is standing up because it's too wide. But you see when it goes through the minimum, suddenly it stands up. But unlike in the previous case, this arch is very unstable. It will soon decay. Remember, this is 1,000 frames per second, so it's decaying very rapidly and flattens out. And after that, the curls are accumulating like crazy and crazy, but nothing is standing up. It's far too wide. Yeah. You want to stand up, but you can't. It's too wide. And the end is, again, rather cool. It's strange that in English, something is cool and something is hot mean more or less the same thing. But anyway, so it's going to finish soon. And the end is indeed cool or hot, as your choice may be. It goes whip and then come in.
The picture was 1,000
frames per second. Yeah, it's
being played back at around 15 frames a second? Or?
Oh, that's an interesting thing. Oh, no, it's played at 1,000 times faster, so it's a real speed, if you like. No, not real speed. Anyway, okay.
Watching 1,000 times slower.
Yeah, that's 1,000. That's what I mean. Sorry. Thank you very much for saving me. And okay, can we have this slide, please? And I'm going to go back to the. This was published in PRL by Hanna Santangelo, 2012. And to summarize, we have a zigzag monolayer and drawn out horizontally, and horizontal geometry, no vertical component anywhere. But when you do that, spontaneously and mysteriously, an arch stands up. What on earth is going on? And this is, again, an anomalous reaction, an instance thereof. But in my opinion, this is even more interesting than a chain fountain. Yeah? And the reason is, in the case of a chain fountain, the external stimulus was downwards, vertical, gravity, and the reaction was upward, but still vertical. So the reaction was happening in a direction linearly dependent on the external stimulus. But here, the reaction, vertical reaction, is happening in a direction linearly independent, completely uncorrelated with the geometry or the external stimulus. So it's even more of an anomalous reaction. You're actually going normal to, it's very strange, it's an abnormal phenomenon, but the normal to the geometry and the physics that would be expected. Okay, so this is even more anomalous.
What if you did that in zero gravity?
Good. So I'll come back to that. And in fact, not long ago, I was contacted by NASA to suggest experiments to send up into orbit. And I'll make a very brief comment at the end about this. OK. So the challenge is, why stand up? Here is the cartoon analysis. I've drawn here this picture of the chain having been arranged and being pulled out like this. And soon, at next moment in time, the point that I denoted by A will come inward to A prime, and the point that I denoted by B will be called in to B prime. Yeah? And that's how you saw the movie work. So you get this kind of thing. Well, at some point, B prime and A prime will align and will just be kind of a 90-degree corner there. But that moment is a crucial moment. It's quite interesting. You see, in that corner, you should, with your mind's eye, see a little rod sitting, because the chain has that singular localized bending stiffness. And if you have a rod like this and tug this end of the rod, suddenly what happens? Well, it just spins. That means that the other end pushes out in this direction. And that's funny, because although I'm pulling it downward in that picture, there is an upward component of that reaction which is going. So in other words, I'm actually pushing the chain upstream by pulling it downstream. Anomalous reaction, thanks to the bending stiffness. So the result is that that's beautiful hump or a curl that's formed. Once that curl is, by the way, that curl has typically a radius, which is exactly that minimum radius of the squeezing of the chain that because it's exactly made by the same mechanism. Of course, it's the bending stiffness that produced this. So these curls start accumulating as this curl sweeps back and forth and keeps accumulating these things. And now curls start piling up. Then what happens? Can I have the camera, please? And can we zoom in? Yeah, if you can zoom all the way in here. Thank you. Even more, even more, even more. OK, so I think that's good. Suppose that you have lots of curls accumulating, yeah, like this. Yeah, you can see. Maybe I should move a little sideways here to center. Lots of accumulation. Now, suppose, and those curls are very small, minimum bending, minimum radius. Now, suppose that I push them from both ends. What's going to happen? Well, they can't bend anymore, so they pop up. Did you see that? So I'm going to do that again, maybe with 2 or 3. Here, I'm going to push, and then it pops up. You see? Pops up. Because it can't bend anymore in this plane. In other words, it's really like a bending, buckling phenomenon. Because it cannot bend anymore inside this plane, it has to escape, and the only escape direction is the vertical direction. It buckles out. Now, when I showed this to Mahadevan at Harvard, he immediately said, but you say pushing, but who's doing the pushing? Well, somebody is doing the pushing indeed, and I'm going to answer that question about the friction. Can I have the slides, please? You see, upstream, there's a lot of zigzag of the chains that are stopped there by friction. You see, if you did this experiment in a totally frictionless smooth surface and you start pulling, and the entire thing will just gently slide toward me, and there's nothing that happens. So something is stopping, and that's the friction upstream. But here, when I pull, this bending stiffness, that mechanism, gives you an upward or the upstream component, which pushes in this direction. And then from upstream, there is friction that's stopping it. So there is actually opposing forces that are going like this. And that's enough to cause the buckling. You can have some more extreme configurations which shows this buckling better. But the long and short of it is that at the very moment, this accumulation of curls pops up. It becomes impossible to bend any further and pops out. If you like, in a slightly metaphorical language, we can think of it as follow fashion. You have those curls that have been accumulating. There's too much of an accumulation, hypersaturation of curvature in a small space inside a low-dimensional manifold. And really, the chain can't take it anymore. So it releases that hypersaturated accumulation of curvature into torsion in going into the ambient dimension. Or even more abstractly, if you want, you can think of, say, some problem whose potential profile is restricted to some, say, vertical plane, or if you like, a low-dimensional manifold. And you have some sort of interesting potential profile up and down. You might have minima, maxima, and so on. But suppose that in the perpendicular direction, in the ambient direction, you are protecting this potential by a pair of, say, little humps like this. You can think of them as dikes protecting that profile. So as long as you are moving very gently along this profile, well, you are within the dikes. So you don't come out, so your problem is purely two-dimensional, low-dimensional. But if there's some catastrophe, for example, there might be a passage where the motion of the dynamic spring is so violent that the dikes are not enough to contain them, then you spill outside of this dike, and outside in this direction, there's a lot of interesting landscape, non-trivial dynamics and so forth, and that's what's happening there. So you have to overcome those, if you like, protective dikes that are constraining you to the lower dimensional thing. But once you go spill out, boom, you go crazy. Okay, now, so far, we have been rather careful with all those experiments. I was putting the chain in a very careful fashion, and I arranged this in a monolayer, constant width, or whatnot. But it turns out that none of this care is necessary. You can do any old thing at random, and this works still. And the reason is indeed very interesting. You see, this phenomenon is actually generic because the only things that we're using in order to produce this kind of phenomenon are threefold. First, I kept saying time and again that you need this singular localized bending stiffness, a very, very heck of a Heaviside function, as I called it, of the chain. And also, you need shocks. You see, if you identify yourself sympathetically with one part of the chain, well, you've been sitting there in some arrangement, spending a very peaceful childhood, not going anywhere, and one day, one morning, boom, suddenly you are pulled into finite speed motion, and that's a shock. And you have to have this kind of shock. But if you're thinking in terms of PZs, this is nonlinear hyperbolic. And then finally, this somewhat more mysterious, somewhat ill-understood supply of critical geometry. And if you have lots and lots of curls, they kind of seed this phenomenon. So because we need only those three things, three ingredients, provided you have those three ingredients, turning the table 180 degrees, you will have this phenomenon. So let me show you an experiment. And can I? No, I don't have to have an experiment. I'll do an experiment first. Can I have the camera, please? I'm sorry for. Let's do a randomized experiment. In order to do so, I'll make a random pile. Yeah, by repeating this fountain experiment in miniature, I'm not paying any attention to what I'm doing. And this is a random pile. Yeah. I call it a random pile, but actually, this pile has one interesting feature, which is that when I start pulling the end out, it will never catch. It will keep coming out because of the way I constructed it. I always kept pouring it from above. I never went under. So it is an uncatchable pile, if you like. Yeah. But apart from modulo this uncatchability, I don't know if there's such a noun in English, this is as random a pile as you can desire for, you can hope for. So in this random configuration, watch what happens when I start pulling the chain. It just stands up. We didn't have to do anything. I mean, it just stands up. So can I have the slide again, please? I'm going to show a movie. Here it is. Again, an experiment was made on my desk and filmed by Will Steinhardt. Let me repeat that all we are doing is to pull the chain out horizontally from a pile. And watch what happens. It takes a while to get going, but once it gets going, it goes crazy. And you see, it stands up. And please notice that this standing chain actually lands on the table and then goes out. Yeah, it's not that it has a very localized arch. And it keeps going on and on. And look how crazily twisted the root is. That's where the curvature is being released into torsion. That's where you're flowing over the dike. Yeah, look at this. Ooh. And there's a lot of criticality in the picture because I randomized it. There are lots of nooks and crooks and curved things, and they're all seeding this standing up, and together with in connivance with the singular bending stiffness. And you think that it's going to lie down, but it's actually just tilting. It's not dying. It will come back and revive like a phoenix, and then keep going and going until then. I think there's something called the Indian rope trick in the world. This is modern physics version, if you like, of Indian rope trick, and you can do it with a $3 budget as well. Keeps going and going. And somebody suggested that I should set this to music and then release it on the maybe Simon sent a website or something like that. Anyway, it keeps going and going, going and going, until at the end, our familiar whoops, nice dynamic that calls you in. Oops, sorry, I shouldn't do that. Okay, can I have the slides, please? So, here we go.
The difference in the way it was twisted in the pile, this kind of twist versus that kind of twist?
Yeah, so it goes back and forth, and that's good. That's good, because if you keep going in one direction, this kind of a seeding mechanism is not optimal. So indeed, randomization is working in our favor. It's really nice. And, if you try to organize it too carefully, you may actually be hampering the mechanism. Now, one thing that I would like to make clear at the end of this analysis is that you might have worried about the actual way in which I conducted the experiment, because instead of actually pulling it out with a pulley or something horizontally, I dropped the chain. And indeed, the chain had to turn a corner on the edge. And that disturbance was indeed disturbing. But I'm going to convince you very quickly that that kind of disturbance has no effect on the main part of the physics. And the reason is, again, a consequence of that key thing that we obtained, and the tension, pulling force equals rho v squared. Why is this? Well, imagine that you have some sort of experiment like this, and chain is flowing, materially flowing, so it's convective in this direction. And then you create some disturbance here, and you want to send this disturbance upstream to sort of spoil the effect upstream. Well, that disturbance has to travel like a chain. But elementary physics says that if you have some system like this, and you want to have the speed of the chain, well, the universal formula is that the speed of the chain is elasticity divided by density square root. But in this problem, the elasticity is precisely tension. Density is rho, that density. And if you take a square root in the light of that formula, you see that that's exactly v. It's getting a bit confusing, but what it means is that when you have this experiment, the substratum of the chain is moving this way at v, and the wave wants to travel, disturbing wave wants to travel upstream at v, but these v's are exactly the same, which means that any disturbance that you create must be a standing picture. It cannot move anywhere because those two speeds exactly are equal by this miraculous coincidence. So you cannot disturb from something like the edge of a chain. All waves that you see are standing waves. So it's sort of strange meaning of standing wave. So the stability of the shape is guaranteed. It's probably a good time to conclude this talk with a little magic show. And can I have your attention? You don't have to have the camera or anything. So here, no, you don't have to have the camera. OK. Here is the loop chain that I've already used, and a ring. Yeah. I'm going to lift the ring from underneath and hold the ring horizontally like so. And when I release my fingers, of course, the ring will go straight through because nothing is stopping it. You know, there's no topology, there's no linkage. Of course, it has to go through. It cannot stop. Yeah? But now, I'm going to prepare exactly the same initial configuration, initial condition, lift the ring and hold it with my fingers. And I'm going to mumble something mysterious in Japanese. Sometimes I'm not mysterious enough, so please forgive me. And when I release the finger, it caught. What? How did it stop? I mean, there's nothing. There's no topology. I mean, it's impossible. Of course, it's impossible. So you probably didn't see it. You are probably dreaming it. And indeed, if you are really careful, and I mean it, if you're really careful, you release your fingers, it goes straight out. Nothing stops it. Yeah. However, if you're not careful, if you prepare exactly the same initial configuration, but at the critical moment, I'm distracted by, for example, my charming photographer, and then I'm not, what? While I wasn't paying attention, something like this happened. So what happened? Yeah, this shouldn't happen. This, because you've been so patient with my talk, I'm going to reveal the secret for free today. This has to do with bending stiffness in some sense. Because, and I'm rather fond of this trick, because you see, most of the magic tricks that you see in the world depend on the magician's supreme dexterity. The magician has to do something extremely precise, and only then an interesting effect happens. But here, it is a generic trick, it turns out. If you do things at random, with probability 1, it works. Indeed. So that's why I was saying carefully. if I support my ring like this with two fingers, in this case, middle finger and thumb, and suppose that I was freakishly careful, so freakishly careful as to release the two fingers at the same time exactly, and then the ring will fall down horizontally and will go straight out, obviously. But in generic situations, I cannot synchronize the release of my fingers. One of the fingers will go first. So suppose that I release my middle finger first. What happens? Well, the other finger is still in contact, so the ring starts pivoting and develops an initial angular momentum and falls down like this. And towards the end, it will go into, let me show you in this direction, goes into this kind of configuration. Now, at this stage, the chain could, in principle, flip over, come through the ring and release itself. But the chain really doesn't want to be flipped hither and thither so quickly because it has bending stiffness and rather singular one at that. So instead of flipping, it wants to slide along the ring. So the chain becomes wider and wider and slides along the ring. And this sliding is an instability process because as the chain widens and slides, it becomes more and more tangent to the ring. That is less and less normal component, which means that it makes it easier and easier to slide, so it becomes easier, and eventually it catches on the other side. Yeah. And that's how this works. So if you are not paying attention, you can do this, and you might be distracted, for example, because I have to continue this talk, and then I'm thinking how to thank everyone at the end. And if I'm not paying attention, so it doesn't work either. Okay, good. So can I have I'm going to go back to the talk. Good. If I may then say something at the end of all this. We all have this impression, adults and the children alike, that science happens in specific contexts, shall I say, in life, in the society. There might be labs, institutes, internet, libraries, classrooms, and between pages of a big treatise, or it might involve great research grants or cutting-edge proposals and all that. And of course, all these things are supremely important. That's where we expect science to come from, and that's how we can run science as a society. So you are justified in asking, how come the experiments like this that I've shown you today, the phenomena like this, how come we're messing around with things like this, and we are actually finding really non-trivial, and shall I say new, applied mathematics in toys of all things of daily life? Yeah? By way of a possible answer, I'd like to present to you a very little-known passage from Aristotle. And it's from De Partibus Animalium. I don't think a whole translation has been published in English. And in this passage, Aristotle is telling an anecdote about Heraclitus. Heraclitus was a pre-Socratic philosopher who flourished around 600 BC, Panther and so on. And he was a great, if you like, a science star of the time, equivalent of today's professor at Simon Center. And two young people come to visit this Heraclitus. And of course, they are expecting to find really a great scholar, maybe with a white beard and a white lab coat, and then lecturing to an entire theater of 1,000 people, or sitting at the supercomputer programming, or deep in calculations with thousands and thousands of pages all over the place. But when they arrive to meet Heraclitus, they find a completely different scene, and they are rather surprised. Here is Aristotle speaking. In all natural phenomena, there is something of the marvelous, he says. There's a story that some visitors once wished to meet Heraclitus, and when they entered and saw him in the kitchen, warming himself at the stove and playing with the children, they hesitated. But Heraclitus said, "Come in, don't be afraid, there are gods even here. Enaigar kai entausa theus." It has been a great privilege and pleasure to address this esteemed audience, and I would like to thank you for your friendly company, and especially I'd like to thank the Della Pietra family, John Morgan, and the staff, and all of the Simon Center for Geometry and Physics for their warm hospitality. Thank you very much for your attention.
Any questions? Maybe I should say more questions. Yes.
Yes, Sriram.
Is there a critical velocity associated to the horizontal problem?
Sriram's question is there a critical velocity associated with a horizontal arrangement problem, either regular or random? Yes, there is. And that velocity corresponds to that condition that you really have to overcome the potential disturbance. So you have to have enough kinetic energy, and that kind of inequality that I suggested will guarantee this to happen. And somebody also, a gentleman in the back, asked what happens in zero gravity or frictionless table. Well, you now know the answer. It's connected with Sriram's question yourself. So if you do it in zero gravity, especially in frictionless context, suppose that I go to orbit and then make the same arrangement, but floating in empty space. And when I start pulling one end, of course, the entire thing will just translate. So it's not going to happen. But you have to, if you can find a way of sort of pulling back, so the background normal reaction, then you will find the same mechanism which will sort of buckle out of the plane, and you'll start going in completely uncorrelated directions. That's my prediction. Pretty sure that's true.
So the reversals were critical for this phenomenon to happen, the direction reversals.
Can you kindly repeat it?
Direction reversals were critical. If you hit it in a spiral on the same spacing, this.
Yeah. So the question is, what happens if you make a different arrangement, for example, in a spiral rather than this zigzag? First of all, if you do it in spiral, the chain catches, unfortunately, so it doesn't work. But in general, the more sort of seeds for those curls you have, the better it is. And somehow monotonic curve will not seed this so well. So really a randomization is one of the best ways of achieving this purpose, it turns out. Okay, so the another comment is that you can have a spiral which prevents catching by sort of changing the landscape on which you lay the spiral. That's an excellent idea. And I try to do this, but actually it's a bit tricky to arrange that experimentally, but I am sure that it can be done also. In fact, in space, you could have, for example, the cylinder floating in space, and you can sort of coil this chain on the inside wall of the cylinder and then pull. That would be nice because as sort of it's pulled out, there's some sort of slight centrifugal force will make it stick to the inner wall. That will provide friction, and I think that will work in 3D as well. Yes, sorry. Sasha.
As this is very generic phenomenon, as you explained, do you know any examples of either application in industry or some natural phenomenon which shows this?
Good. The question is, well, I claim that this is generic, and indeed it is. And so are there already applications? This is quite recent, so I haven't really thought up of applications yet. I'm playing with some toy ideas, if you see what I mean. But I think that this is something that at least we should be aware of. The presence, or if you more positively, perhaps methods of manufacturing, realizing anomalous reactions in all sorts of situations. And provided you have some sort of singular material property and shocks, and some criticality, you can get, there's a chance of doing not only anomalous sort of force reaction, but anomalous torque reactions, anomalous all sorts of reactions. In the meantime, there is already one application. You know, whenever I give talks like this, of course, I like to share this with the maximum number of people. So people say, well, what are the applications? Does it have any practical applications? One practical application is that when I show this to children, they seem to be very happy.
So you were explaining that if the width was too much, if the seeds were too sparse, it wouldn't work. So is it a function of, let's say, I mean, you sort of want a high seed density. Is it a matter of time or length? Like if you sped it up really quickly,
okay,
you have like some dissipation.
Right. Yeah, so the question is, what about this sort of, in connection with this claim about the width constraints? So you have to work within a certain window. And as I kept saying, I'm sorry, rather metaphorically, you need seeds. Well, but seeds in terms of what scale? Is it time scale and length scale? What? It is really the following phenomenon. The reason, it's a bit more complicated than this, but I'd like to give you the cartoon picture. If you have a too wide an arrangement, what happens is that curl starts, but it has time, shall I say, to resolve itself before it reaches the other end, the curls and bumps into the next curl. And then you have an accumulation of two curls, and it resolves itself, and so you don't get an accumulation of curls, and so you don't get this kind of situation ready to buckle. And so you have to make sure that something happens without leaving time, if you like, or distance for the nascent singularity to resolve itself. So if you like, it's a matter of speed or matter of sort of distance. It's a combination of these things. But you have to sort of catch the moments and keep accumulating those curls, and otherwise it doesn't work.
Instead of just using gravity to pull down your train,
Yeah.
you sort of like attach it to some motor.
That's it. So if you go really fast, you are more likely to sort of catch it before the singularity resolves, so it will work much better. And I try to pull it out at some different rates and even at non-constant rates. It's a very, very robust phenomenon. And I haven't quite figured out what are the qualitative bounds on the realization of this phenomenon.
If you had a strip of cable and then ice on the outside, you could make much longer cycles.
Interesting. So you can have a variable, non-constant friction on the table, and that is, of course, an interesting variation that you can consider. Indeed.
You think that this sort of singular bending energy is generic somehow? Because if you had something like a rope, no matter how thin it was, it still would be.
The question is, how common is this singular bending stiffness? Well, this is a physics problem, so you really have to talk about the scales. But it's pretty good. I talked about this work at MIT at some point, and then there was one professor who had a yacht in the Boston Harbor, and he told me that he tossed the anchor overboard with a chain following, and then he saw it rise as well. Now, there is no movie to go with it, so it's just second-hand story. I'm sorry, but and with ropes it works, but nice tough ropes. On the other hand, if you have sewing thread or something like that, a very thin one, well, then you can really bend it almost to zero curvature, and that's not enough. So you have to have this singular behavior at some point, at some minimum and finite, non-zero finite minimum, you have to stop bending and put up an infinite resistance. You see, because this, how much you resist below a certain curvature is really corresponds in that abstract picture to how much you're willing to spill over that dike. Yeah? Dike is preventing, it wants to stay horizontal, it wants to stay low dimensional, but the fact that it can go into the ambient dimension, release itself, really has to come from somewhere. And you have to get stuck in order to do this, and that getting stuck is how hard that bending stiffness is, how localized and singular it is.
Yes.
When we watched the video, it tried to stand up and then it fell back down. Does that always happen, or?
Good and rather embarrassing question. So the question is, when we watched the first video, the first movie clip, the chain tried to stand up and failed, and second time it stood up. I don't understand the phenomenon in that detail. I think that somehow, this is a tautological answer, but somehow the conditions weren't right the first time. I don't know how it works. On the other hand, as I showed you in the last movie clip and the experiment just before, it works also generically. So, just catches whatever is available, stands up. But I don't know when exactly it stands up and when it doesn't.
One last question. Yes.
So if you do the same experiment with chain of atoms, since the L is not a parameter here, so it can really go down to quantum level.
Yeah. The question is, what about the atomic analog of this? What about the chain of, say, molecules or even atoms and so on? I don't know. I haven't done the calculation, and for the time being, I've been exploring the macroscopic scale. But if you want to sort of explore it with us, it would be wonderful.
I think